Okay, so now we know how to get the equations of lines in 3-space and planes. So let's look at some more examples with those. What if I wanted to find the intersection of two lines in 3-space? Well, we have three possibilities. These lines could intersect at a point. They could be the same line, which would be infinite solutions. I guess we do have four possibilities. They could be parallel, where there's no solution. And they could also be skew, which means they don't intersect and they're not parallel. So we've got all those different possibilities. So let's start with the assumption that these two lines intersect. And let's figure out how to solve this. So if the two lines intersect, think about how you would do this in 2 dimensions. How do two lines intersect in a plane? Well, we would solve a system of equations. So let's do that. So let's take any two, it doesn't matter. Let's use the x's and the y's, and let's set those equal to each other. So 1 plus 2t equals 2 plus s. And by the way, we're using t in one and s in the other because we can't use the same parameter. We have to use a different one for each because these are two different lines. Then I'll set the y's equal to each other. So 3 plus 2t is equal to 6 minus s. Now, I picked the x and the y equations. You could use the x and the z's or the y and the z's. Doesn't matter. Just pick two of them. We'll solve this system. We'll get a solution for s and t that'll make x and y's equal. Then we're going to have to plug in and see if the z's are also equal. And if they're not, then we don't have a solution to this system. So, how do we solve this one? Well, I think elimination would be really easy. We'll just add the two equations together. And we get 4 plus 4t is equal to 8, and the s's cancel out. So then when I solve this for t, I'm going to get t is equal to 1. Now take either equation and plug t equal 1 and solve for s. And I'll use the first equation, so we get 3 is 2 plus s, so s winds up being 1 as well. Now that's just a coincidence. They won't always be the same value, of course. All right, so when t is 1, let's look at the first equation. The first equation, when t is 1, we're going to get x is equal to 3, y is equal to 5, and z is equal to 1. In the second equation, if s is equal to 1, plug that in and I'll get x is equal to 3, y is equal to 6 minus 1 is 5, and z is equal to negative 2 plus 3 is 1. Notice we got the same value for x, y, and z when t is 1 as we did for x, y, and z when s is 1. So that tells us that the point 3, 5, 1 is where these two lines intersect. And that's the only solution. So they're not parallel, they're not skew, and it's not the same line. All right, let's look at another one. Determine whether these two lines are parallel, intersecting, or skew. Okay, so similar idea. So the first thing we need to do is recognize this is in the Cartesian form, or sometimes called symmetric form. And so let me rewrite each of these equations and put it in the parametric form, or let's put it in the vector form. So the first one, let's write as, we're going to have what? X, y, and z equals, and we're going to have 0, 1, and 2 plus, and I'll use t as my parameter for the first one, and we get our vector 1, 2, 3. That's the direction vector of our line. All right, for the second one, we have x, y, z equals, the point is going to be 3, 2, and 1. And I'll use s for the parameter for this one. And then our direction vector is negative 4, negative 3, 2. All right, so the first thing we want to notice is the direction vector for these two lines. 1, 2, 3, and negative 4, negative 3, 2. One of those is not a scalar multiple of the other, so that tells us that our lines are not parallel. So I can't multiply the vector 1, 2, 3, or multiply the other vector, doesn't matter which way. One is not going to be a scalar multiple of the other, so we're not parallel. That's the first thing you should check, and that's the easiest thing to check. All right, so if they're not parallel, maybe they intersect. And then if they do intersect, we'll have our answer. If they don't intersect, then by default it must be skew. So let's go ahead and do what we did in the last problem to find out. So I have, let's set the x and y equations equal. So I'm going to have, we have x equals 0 plus 1t. So 0 plus 1t equals 3 minus 4s. And then I'll set the y equations equal. Y equal 1 plus 2t, and the other y is equal to 2 minus 3s. All right, so 0 plus 1t, I could just write that as t. And so instead of using elimination this time, I think I'll use substitution, because it's set up for that. And I'll plug 3 minus 4s into t in the second equation. And I'm going to get 1 plus, I have to distribute the 2, so 6 minus 8s equals 2 minus 3s. So move that over there, I'll get 5s equals 5. So s is equal to 1. And if s is equal to 1, then t, if I plug s in, I'll use the first equation, plug 1 in for s, 3 minus 4 is negative 1. All right, so that's what I got. So now let's go back up to our equations, and for the red one, I'm going to get, now I'm plugging in negative 1 for t. So I'm going to get x equals negative 1. And then in the y equation, if I plug negative 1 for t, I get 1 minus 2 is negative 1. And then for z, I'm going to get 2 minus 3. I also get negative 1. So that's kind of unusual, but unusual things happen. Okay, now I'm going to plug in 1 for s in the other line and see what I get for x, y, and z. So when I plug in 1 for s, I get 3 minus 4 times 1, so that's negative 1. And I do it for y, I'm going to get 2 plus negative 3, so that's also a negative 1. Now, obviously, x's and y's are going to match because we set up our system by setting x's and y's equal. But the real test comes in with z, and do we get the same z value? So let's see, if I plug in 1 for s, I'm going to get z equals 1 plus 2s. I get 3. So those are not equal, so that tells me that there is no solution, so these lines do not intersect. So the direction vector of the lines, one was not a scalar multiple of the other, so they're not parallel. And they don't intersect, there's no point of intersection, so by default, these two lines must be skew. Let's look at another one. Find the intersection of the line and the plane. Okay, so visualize what's going on here. We have a line intersecting a plane. So I guess we do have some different possibilities that it could intersect at a point, making any kind of an angle with the plane. Doesn't have to, it looks like it might be a right angle, but it doesn't have to be. If the line is in the plane, then there would be infinite solutions. It would be the line itself. Or the line could be parallel to the plane, and then there would be no solution. So let's start with the assumption that it's going to intersect at a point. And so how are we going to find that point? Now, realize this. What does that mean? That means that the point, the coordinates for that point, the x, y, and z numbers, have to satisfy the line, but they also have to satisfy the plane. So once again, this is a system, and I can kind of set them equal to each other. So here's what I'm going to do. I'm going to plug in 1 plus 2t for the x, and I'll plug in 4t for the y, and 2 minus 5t for the z, and I'll solve this system. So I'm going to get 3 times 1 plus 2t plus 2 times 4t. And notice now, we're just going to have one variable to solve for, plus z, which is 2 minus 5t, plus 4 equals 0. So when we simplify this, we're going to get 6t, and 8t is 14t, minus 5t is 9t. And then 3 plus 2 is 5 plus 4 is 9 equals 0. Solve for t, we get t is equal to negative 1. So this tells me that when t equals negative 1, I'm going to get a point on this line that should satisfy both the line and the plane. So let's go ahead and plug in t equal 1 to my line. You know, and granted, this will take a little thought, so you may need to actually work through this again just to get the conceptually why I'm solving the system this way and why we get a solution. So when t is negative 1, I'm going to get x equals 1 minus 2, okay? I'll get y is equal to 4 times negative 1, and we'll get z is equal to 2 plus 5, which is 7. So therefore, the point negative 1, negative 4, 7 is the intersection of the line with the plane. Now, can I verify this? Sure, that's easy to do. I can go ahead, let's erase some of this stuff so it's easier to see what I'm plugging in here. All right, so if I plug in negative 1, negative 4, 7 for x, y, and z, you're going to see t is negative 1, so we know that works. Let's test this in the plane and see if that works. So 3 times negative 1 is negative 3, plus 2 times negative 4 is negative 8, that's negative 11, plus 7 is negative 4, plus 4 is 0. Check. So that point is both in the plane and on the line. And so we have our solution. Okay, what if we want to find the angle between the planes? So this is an interesting one. And so what I think the best thing to do is to visualize, let's say if you look at the corner of the room you're in, and you've got where two walls are meeting. All right, so that's the line there. So I want to find the angle between two planes. So if you're looking at the corner of a room, we're trying to find the angle between the two sides. So depending on how you're viewing this, I'm looking for the angle from one wall between the two walls. All right, so what information do we have? Well, we have the equation of two planes. Now, from each plane, we know the information that we can get from that is a normal vector to the plane. So we have 8, 1, 4. Is perpendicular to one of the planes. And then we're going to have 2, negative 2, 1. And that's normal to the other plane. Which, by the way, therefore tells us that our planes are not parallel, because if one's a scalar multiple of the other, then you know that the normal vectors are parallel, which means the planes must be parallel. So we have these two vectors. So let me see. I think I'm going to draw my corner of my walls this way, maybe. No, that doesn't help. Oh, I know. Here. Let's get a better picture for you. Art was not my forte. Maybe that helps. Okay, so we're trying to find the angle, and here I'll mark the angle down here. We're trying to find that angle. All right, so we have these two normal vectors. So one vector is coming out of this plane, and the other vector is coming out of the other wall. And so these are the points where they touch the walls. So if you were standing in the corner of a room and you had, let's say, two rulers, and you held each ruler perpendicular to each wall and made the rulers touch, come out of, out into the room and touch at a point. That's what I'm trying to draw here. So I think when you do that, you would agree that we have made a parallelogram, and the angle, I guess I could do this as a dashed line. I should do it in blue. That the angle between these two normal vectors is the same as the angle between the two walls. So in essence, if I can find the angle between the two normal vectors to the planes, I'll find the angle between the two planes. And we know how to find the angle between two vectors. We actually had a nice equation for that, and that was the cosine of theta, theta being the angle between the two vectors, is equal to the dot product, so 2 times 8 plus 1 times negative 2 plus 4 times 1, divided by the product of the magnitudes of the vectors, so 8 squared plus 1 squared plus 4 squared, times 2 squared plus negative 2 squared plus 1 squared. And so therefore we've got theta, the angle between the vectors, which is going to be the angle between the two planes, is equal to, what do we get? So we get 16, 20, so we get 18 over the square root of 81. 4, 7, 4, 81, right? So that's 9. And then the square root of 4, 8, 9. Well, that works out nicely. So we get 18 over 9 times 3. And, oops, let's keep it here. So the cosine of theta is equal to 2/3. So theta will be the inverse cosine of 2/3, which is approximately, let's check on the calculator. Let's make sure we're in degree mode. And get the calculator up and running. Stay with me. There we go. We are in degree mode. So second cosine 2 divided by 3. So the angle between the two normal vectors, and consequently therefore between the two planes, is about 48.2 degrees. And there you go. All right, let's look at another problem. Find the distance between these two planes. Now, this is where it gets a little interesting, and some textbooks will go through a whole long process of showing how to find the distance between a point and a plane. And if you understand that, well then if the planes are parallel, and obviously if these planes are not parallel, then we can't say there's any distance between the two planes, because that distance is changing, and at some point, or actually at a line, the planes actually intersect. So we need to make sure that these planes are parallel, and sure enough, they have the same normal vector, so we know that these two planes are parallel. So therefore, we want to find the distance between them. Once again, my fantastic artistic ability comes into play. All right, so we want to find the distance between these two planes. Now, there's a nice formula to figure out the distance from a point to a plane. And so if we could just come up with a random point in one of these planes and then use the other plane equation, we could use that formula. But that's way too much work. So let me give you a shortcut to this. It turns out that to find the distance between two planes, we're going to take the difference of the d values. Now remember, those are the constant terms. So that's going to be there. The distance between the d values divided by the magnitude of the normal vector. Now, these equations have to have the same normal vector. If, let's say by chance, somebody tried to get tricky with you and said, oh, you know what, this plane is actually 24x minus 8y plus 6z minus 26 equals 0. Well, that's the same plane as this one, but I multiplied it by 2. So what I need to do is I need to make sure that we have the same components of the normal vector to both planes before this process will actually work. So, and we do have that already, so we're fine with that. So then, in terms of words, it's the difference between the d values divided by the magnitude of the normal vector. All right, so the d values are -5 and -13. Well, what's the distance between those? Or the difference between those? So -5 minus -13. Take the absolute value because we're talking about the distance. I'm sorry, the difference, which is like a distance between two values on a number line. So that's going to give us 8. And then the magnitude of the normal vector, and the normal vector were our coefficients of x, y, and z. So 12, -4, and 3. 12, -4, and 3. So we need to find that, which is going to be 12 squared, 4 plus -4 squared, plus 3 squared. And that winds up being a perfect square, which is 13. And so the distance between the planes is less than 1 unit. They're less than 1 unit apart. It's 8/13 of a unit. And that's all you need to do. Sometimes you will see a process called normalizing a plane. And so what they do there is they actually find the magnitude of the normal vector, the 12, -4, 3, which in this case is 13, and then they multiply the equation by 1/13. So you wind up getting 12/13 x minus 4/13 y plus 3/13 z minus 5/13 equals 0. And then same with the other one. And this time we get 13/13, which is 1. And then we just, now all we have to do is find the difference between these constant terms, which happens to be 8/13, which is what we already have. All right, let's look at one last example. Let's find the intersection of these planes. All right, so let's picture two planes intersecting. If they intersect, they're going to intersect at a line. So I guess that's one possibility. They intersect at a line. Another is that they're parallel. Well, if they're parallel, their normal vectors will be scalar multiples of each other. And the normal vector for this one is 1, 1, 1. And for this one, it's 1, -2, 3. So I know that these two planes are not parallel. So I don't have to worry about that, where the answer would be no solution. And they're obviously not the same plane as well. So my answer is going to be a line. Now, what do we need to get the equation of a line? Think back, a line in 3 space. We need 2 things. We need a point, and we need a direction vector. So, how are we going to figure that out? Well, let's start with the direction vector. Now, we have 2 planes that intersect. So, picture, let's say, if you pick like the ceiling and a wall in the room you're in, and you take a ruler and make it normal to the ceiling, perpendicular to the ceiling, and a second ruler perpendicular to the wall, and make those rulers touch. Okay, we've created a rectangle. Now, the intersection of the ceiling with the wall is that crease where they meet, that line where they meet all the way across. Now picture those 2 rulers that you're holding normal to the ceiling and to the wall. Those 2 rulers determine a plane. What happens when you do the cross product of those 2 vectors, those 2 rulers? You're going to get a vector that's perpendicular to the 2 rulers. And if you actually need to try this, it might be a good idea to actually try this. But you're going to see then, if you have a third ruler that you make perpendicular to the first 2, you'll see that that ruler is parallel to the line of intersection where the wall and the ceiling meet. So that's going to be the idea. That's how we're going to come up with our direction vector. So let's start with that. If I do the cross product of these two normal vectors to the plane, that's going to give me a vector that's parallel to the intersection of the planes. And that's what I need. I need a direction vector for where these two planes intersect. So I need to do the cross product. And so when I do the cross product, what am I going to get? You can work through the steps if you need to, but you're going to get 5. And then cover that up, we get 3 minus 1 is 2. You should get -2, and then -3. So 5, -2, -3. Now, I'm trying to come up with the equation of the line. I'm going to go ahead and start to write my answer over here, just so I can keep track of all this. My answer should be a line, which I'll write it in vector form. So my point is going to go in here. And then my direction vector, which I just figured out, goes here. All right, so now I still need to figure out a point. Now, any point on where these two planes intersect. So any point on the line where these planes intersect is going to be our solution. So one idea, and it takes a little while to visualize this, but what if we looked at, picture these two planes in 3 space, and the intersection of these two planes is going to be a line. That line probably will intersect the xy plane. I'll say that again. The intersection of two lines, picture two planes in 3 space, and picture where the two planes intersect, and that's a line. Now, if we could just get rid of the planes and just picture that line probably is going to intersect the xy plane. If it doesn't, then it'll intersect the xz plane or the yz plane. So we're just going to pick the xy plane. And in the xy plane, all points have one thing in common, and that's z is 0. So that's what I'm going to use. I'm going to set z equal to 0. And likewise, we could have set x equal to 0 or y equal to 0. It doesn't matter. When I set z equal to 0, the equation of my first plane becomes x plus y plus 0 equals 1. And that's a line in the xy plane. And then in the second plane, if I plug in z equals 0, I'm going to get x minus 2y plus 0 equals 1. That's another line in the xy plane. The intersection of those two lines in the xy plane will give me a point, and that point is on the intersection of the two planes from the original problem. You might have to play this back a couple times to get all of this. Okay, so let's solve this system. So I have x plus y equal 1 and x minus 2y equals 1. And let's use the elimination method. I'll subtract. So the x's will cancel out, and I'll get 3y equals 0. So it turns out I get y equals 0. Not always going to happen, but that's fine. And then if y equals 0, I can plug that into either of these two equations, and I'm going to get x equals 1. So I found out that z equals 0, y equals 0, x equals 1. That's a point that's on both planes. So let me go over here to my point, and I have 1, 0, 0. Oops, 1, 0, 0. So now I've got my point. I already figured out my direction vector, and now I just need to use that point, and I can plug that in right here. And this is the equation of the line, which is where these two planes intersect. And you can check that point, 1, 0, 0. Works in the equation of that plane, and it's also in that plane. So I know the point 1, 0, 0 is in both planes. I found my direction vector by doing the cross product of the normal vectors of the plane, which gave me a vector that's parallel to the intersection of the two planes. And with those two pieces of information, I was able to write my solution, which is a line.